I want to thank the organizers for inviting me. I think that the opportunity to get people working on the geophysical fluids and astrophysical fluid sides together, share ideas, is really exciting and doesn't happen often enough. I'm going to talk about natural variability, modes of natural variability. I'm going to focus on the climate system, which is where I am working. This is work that I've done with Baylor Fox Kemper, Roy Zia, Aaron Nelson, and Dibyendo Mandal. They seem to have two microphones. And so the best known of the climate variability is El Nino. This is the Earth. This is North America. This is the tropical Pacific. And the system fluctuates between states of warm tropical Pacific, which is an El Nino state, and cooler tropical Pacific, which is a La Nina state. But these kinds of spatiotemporal oscillations, what I'm going to argue today is they're ubiquitous in the kinds of systems we're interested in. And so I stole this picture of a magnetic wreath. Yuri Tumre spoke about these a couple days ago, and this is from a paper with Ben Brown and collaborators. And so this is an example on, I believe they were some small stars of some kind. This is the extent of my astrophysics knowledge. But we see these spatiotemporal patterns pretty much everywhere we look. And so geophysical and astrophysical systems, they're complex systems. We know the laws governing them for the most part. We know they're governed by fluid dynamics, radiation physics, chemistry can be important sometimes. They're turbulent multi-scale systems. The climate system goes from roughly a meter to 10 to the 7 meters. The temporal scales are from 10 to the 3 to the 10 to the 8 seconds. We've got a very complex mean state. It's a statistical steady state, and there are fluctuations about that statistical steady state, and it is a thermodynamically non-equilibrium steady state. Now, we often talk about turbulence as being in equilibrium, and by that we often mean the same thing as it being in a steady state. And we don't usually make the distinction between thermodynamic equilibrium and thermodynamic non-equilibrium, because when we're talking about turbulence, it's pretty much always thermodynamically non-equilibrium. But I'm going to try to make that distinction today because I'm going to draw on some ideas from thermodynamics of non-equilibrium states. And the important thing is that the fluctuations about this mean state are self-organized into preferred spatiotemporal patterns. And it's those preferred spatiotemporal patterns that I want to talk about. So the climate system is a non-equilibrium state in the sense that it's connected to two thermal reservoirs. It's forced by black body radiation from the sun at roughly 6,000 Kelvin. It is damped by outgoing long-wave radiation to the 3K background radiation of the universe. It emits at roughly 10 microns, and it is the balance of that incoming and outgoing radiation that leads to this thermodynamic non-equilibrium steady state. Climate variability is really important for the climate system. I think it's probably important for all the kinds of systems we're interested in here. Extreme events are obviously really important. Those of you who are from the East Coast of the US are thinking about a particular extreme event over the next few days. One of the interesting things is that our observational records are typically too short to really determine a lot about the PDF of these kinds of events. Climate models do a really good job of capturing the mean state. They tend not to be as good at capturing the variability. And so whereas we can run climate models for a long time to get the PDF, we don't trust the PDF as much as we do for the mean state. And very small changes in the mean can lead to large changes in the probability of extremes. This is observational data of temperature distributions over various decades in various cities, 1950s, 1960s, et cetera. You can see the PDF has moved to the right. This is climate change of about a unit of 1. These are units of standard deviations. But the important point to notice is that that this relatively small change in the mean state, well, first of all, the distribution has gotten broader. You can see because the peak goes down, and these are normalized PDFs, so it must have gotten bigger. But the probability of this tail, 3 standard deviations, 4 standard deviations, even 5 standard deviations, has just become enormous compared to what it used to be. And so these extreme events are crucial for the planet we live on. And so when I say that this variability takes the form of patterns, that we're used to spatial patterns. I've done a lot of work. A lot of you have spent a lot of time thinking about coherent structures, coherent vortices, jets. And so, for instance, this is a satellite image of the ocean off of Tasmania, and you see these nice vortices. This is an image of the jet stream. But there's a lot of interesting spatiotemporal variability of these structures. This is a hurricane. These are currents and vortices in the ocean, and this doesn't show up as well, but I'm sure you've all seen these absolutely amazing images of Jupiter showing the vortices near the pole. And so the variability in the climate system takes the form of what the climate community has taken to be calling oscillations. These are preferred spatiotemporal patterns of natural variability. I've learned to accept the term oscillations. It's not an oscillation, you shouldn't think of a pendulum. You shouldn't think that the power spectrum of these guys has a really nice sharp peak. These have very broad, relatively broad power spectrum. They're certainly not 1 over F. You can see a peak. El Nino, for instance, the El Nino Southern Oscillation, has a peak in the power spectrum from, say, 3 to 7 years. It's a nice, rounded, broad peak. So they have preferred time scales. I don't really think of them as oscillations. They're not very regular. They're very irregular. Another oscillation, which is one I'll talk about, is the Madden-Julian oscillation. This is a time longitude plot of sea surface temperature, and this is kind of the standard way to look at El Nino. And so what you see is that there are these regular oscillations. Well, every year you see this red comes out a little bit, and part of that is the annual cycle. Every year it gets warmer, and every winter it gets colder. And so if you subtract off this mean annual cycle, you get the anomalies, and this is where you really see the extreme events. So this is a particularly warm event. This is the recent, you can't see this, 2015, 2016 El Nino. Then there's periods where not much unusual is happening. You just have the regular annual cycle. Then you have these cold periods. This was the 1996-97 El Nino. And so these are the patterns of climate variability that take the form of the El Nino Southern Oscillation. The Madden-Julian Oscillation, we'll look at it a little more. This, again, is time and longitude. Here we're looking at a particularly filter of the outgoing long-wave radiation, and you see these patterns moving up. Actually, time goes down in this one, and so they're moving down and to the right. And there are other oscillations. There's something called the Pacific Decadal Oscillation. There's the Atlantic Multi-Decadal Oscillation. There's many others. Each oscillation has very different detailed dynamics, and I'll talk about that again, and it has very different spatiotemporal timescales. And so in that sense, they have nothing in common. Kinds of turbulent fluids we're interested in are very high-dimensional dynamical systems. And these oscillations tend to occur in subspaces of the dynamics, often very, very small subspaces. They dominantly project on a very small number of degrees of freedom. And I think this is what makes them so readily apparent when we look at visualizations. They don't look random. They really jump out because there's a few modes that are actively excited. And they typically bleed over onto all of the rest of the degrees of freedom. They're not isolated. And as far as I know, there's no formal mathematical reduction that people have really done to prove this. So El Nino, and so has a time scale of several months to years. It projects onto the large scale sea surface temperature. tropical sea surface temperature, so that's SST. It projects onto the ocean stratification. One of the features about the Earth's oceans is there's a layer at the top that's less dense, and the deep ocean is very dense. There's a relatively sharp boundary between them, and that boundary can move up and down. And the location of that boundary is one of the things that El Nino impacts. It projects onto some atmospheric circulations called the Walker circulation, but then it affects rainfall and temperature around the globe, which is one reason why we hear about it in the media so much. If there's an El Nino, then that impacts rainfall in California and the rest of the world. Madden-Julian oscillation, on the other hand, time scale of weeks to months versus months to years, so much shorter. And this is dominantly projects onto the outgoing long-wave radiation. And outgoing long-wave radiation is a particularly convenient variable because satellites do a really good job of measuring how much radiation is coming out of the Earth. And this is really important for tropical convection. So the MJO is really another one of these dominant patterns of natural variability. Climate models have a really tough time with both of these. I don't think climate models right now are have any real skill at capturing the Madden-Julian oscillation. El Nino, the models sort of do okay sometimes. If you talk to the modelers, they always say, oh, our new model is much better. But if you ask what's going to happen to El Nino under climate change, the models give very divergent answers. We characterize in the climate system these oscillations by indices. And this is the sense that we think of these phenomena as projecting onto a low number of degrees of freedom. And so we typically create a filter of the high-dimensional data. It's empirically constructed. And so if you were going to think about, say, trying to create an index for magnetic wreaths, it would require spending a bunch of time really understanding what the dynamics looks like. And so these are spatial and temporal averages of very carefully selected variables. It seems like a lot of black magic when you first look at it, and there's lots of different indices. They're empirically designed to capture the important feature of the oscillation. And so if there's something that a particular scientist wants to grab about the phenomenon, they design an index to capture that. Most of these indices are one dimension. But I'm going to focus on the interesting thing is when you start having multidimensional indices. So for El Nino, the indices usually take monthly mean data because the time scale of El Nino is months to years. And so you want to filter out the daily fluctuations. There's a variety of sea surface temperature indices. The Nino 3 index is one of the most common ones. That's a particular box in the tropical Pacific, and you average the sea surface temperature over that box. Other people choose a different box, the Nino 1 index. Some people like a different box, the Nino 2 index. Other people like, there's a bunch of these boxes. The thermocline depth, the depth of this boundary between the warm upper ocean and the cold lower ocean is called D20. Whereas for the Madden-Julian oscillation, typically one uses daily data. It's bandpass filter, outgoing long-wave radiation, and then they project onto these empirical orthogonal functions. So there's these recipes for creating indices, and that gives you the picture of these oscillations. And the question, of course, is for the various astrophysical patterns of variability that people have talked about here, have people created indices? Could you create indices? So this is an animation of the observed outgoing long-wave radiation. On the top is what the satellite actually sees. Well, that's probably not quite right. And then this is the kind of filtering that's done to capture the Madden-Julian oscillation. And so you can see that there's a lot more going on than just this extremely filtered data. And maybe you can do bandpass filtering by eye and see that this is in here, but I have a hard time with that. But this is the kind of thing that pops out. And there's always questions of, is this real or is this just an artifact of carefully filtered data? And so you have to be a little bit careful that you're not fooling yourself when you do these kinds of things. But so this gives you some idea of what things really look like. So now I want to draw this contrast between detailed dynamics, the kind of dynamics that in the atmospheric dynamics community people really focus on, and thinking in terms of statistical mechanical ideas. So if you're thinking about El Nino, most of the people who work on El Nino think about the detailed dynamical processes that lead to El Nino. So there are these Kelvin and Rossby waves, and the Kelvin waves do one thing and the Rossby waves do others, and these waves are linear waves that come out of calculating dispersion relation for linear stability, linear wave theory about various basic states about the tropical Pacific, and then you include the trade winds and the Walker cells, and the winds do this, and then it pushes the water up that way, and it makes it cold, and then the wave goes, and then this and that. It's this whole sort of tinker toy picture of the dynamics of El Nino. And so the people who do this have all this expertise in these particular dynamical processes. Whereas if you're studying the Madden-Julian oscillation, you don't think about any of this. You're thinking about tropical convection and how the storms work and how the storms perturb the tropopause and how that generates waves in the stratosphere. And there's a whole different set of detailed dynamics on different time scales with different practitioners who have different areas of expertise. And so the analogy would be, if instead of doing statistical mechanics in this room, you were standing on a molecule, standing on a nitrogen molecule, and there's another nitrogen molecule coming and it's about to hit me, but then I move to the left a little bit and it misses me, and then this nitrogen molecule comes in, it hits me and pushes me over here. And we obviously don't do that. The reason we don't do that in part is because this is all happening in the molecules on the time scale of nanoseconds to milliseconds, and we're thinking about things on the time scale of, I turn up the thermostat and 10 minutes later it's warmer in the room. In the climate system, we live on this time scale. These things are happening on the time scale of months to years. And so we can see these waves coming and we care about them. But we can also choose to expand our view. And so by thinking about these dynamics, it hides the commonality among these different patterns of variability. And so this brings us back to this idea of that the climate system is in a non-equilibrium steady state. This ignores solar variability, which obviously is not steady. It ignores volcanoes, which are occasional intermittent bangings of the system, anthropogenic forcing. But there's a number of features of non-equilibrium steady states. The energy input is distinct from the energy dissipation. You can think about you're connected to 2 temperature reservoirs instead of 1. You end up with fluxes of heat, momentum, chemistry. You have interesting fluctuations that are different than the kinds of fluctuations you have in an equilibrium steady state. There's entropy production, violation of detailed balance, violation of time reversal symmetry. But the thing I'm going to focus on is that you have probability currents in phase space, and they define the patterns of fluctuation. So for our purposes, we can think about Kolmogorov turbulence, where the energy input is at large scales, the energy dissipated at small scales. That results in an energy flux, which is the cascade. These are 2 stochastic systems. This one is in thermodynamic equilibrium, if I can get it to run. And you see this is what you would think of as a random walk, just wanders around. This, on the right, has the exact same steady state PDF, but it represents a non-equilibrium system. And you can see that there is a preferred rotation in this phase space. And that's the kind of distinction I'm talking about. If you look at the data for El Nino and plot it in this 2-dimensional phase space, you see these nice patterns of rotation. The Madden-Julian oscillation has these nice patterns of rotation. Typically, people have made these plots and said, oh, look at that. There's a rotation in phase space. How interesting. Our goal here is to quantify this rotation, to find a technique that we can use. And so it's actually relatively straightforward. If we imagine an ensemble of systems in phase space, and those systems, so I've got a collection of particles, and those particles all rotate, I could imagine if those particles were massive particles, I could calculate the angular momentum associated with that rotation. And so we're going to calculate the probability angular momentum. And so it's just the phase space position crossed into the phase space velocity multiplied by the probability density. And what's interesting is it's directly related to the time-lagged correlation. Time-lagged correlation is something that it's very easy to calculate. A lot of people study it. Linear response theory typically focuses on the symmetric part. This angular momentum is the anti-symmetric part. And what's nice about this is, I can go talk to a seagoing oceanographer, the kind who take expensive pieces of equipment and throw them over the side of boats never to be seen again. And if I start talking about phase space, their eyes glaze over. But if I talk about time-lagged correlations, they can get a handle on that. And so one of the things this does is this lets you characterize these phase space oscillations. It lets you compare how do the patterns differ from model to model. How do you compare oscillations in one model to another, or models and observations? And so I'm going to use this to look at simple stochastic dynamical models, in particular Langevin models, which are the simplest stochastic systems that describe nonlinear, that describe non-equilibrium steady states. They are linear systems. They're often used in the statistical mechanical community to capture non-equilibrium states. They're also skillful in modeling some climate phenomena. And my perspective here is that they provide a null hypothesis for these spatiotemporal patterns. And again, the climate models do pretty well with the mean. They don't do a great job with the variability. Observations are not really long enough. And so we don't have a good null hypothesis for what the heck is going on with something like El Nino. How will it change under climate change? And so that even a not terrible null hypothesis would be useful. And the question is, do these linear Gaussian models do that? And so I'm going to skip a few things about how we construct them. And I'm going to go right here. And so we can take these linear Gaussian models. These are two-dimensional stochastic differential equations. You can run them for almost an infinite amount of time on your watch. And you can calculate this PDF of the angular momentum. And what I have here for El Nino and the Madden-Julian oscillation, the yellow is the Monte Carlo of the stochastic model. The blue is the PDF of the angular momentum for the data. And you can see it's kind of chunky. So this line represents one event in the data set. This line represents two events. And this gray is where the two overlap. And you see that, first of all, that these distributions are asymmetric. The ENSO angular momentum is preferably negative. And so we saw in the picture that it tends to rotate clockwise. And that's what we're seeing here. But there are times when it reverses. That's the sense that this is, if you did this for a simple harmonic oscillator, this would be a delta function. But this is very broad. The Madden-Julian oscillation preferentially rotates the other direction. The units of this angular momentum are really weird. It's the same units as diffusion. It's a length squared over time. And because these indices usually have weird units, so for ENSO, the units of sea surface temperature are degrees C, thermocline depth is centimeters, and the time scale is months, so this is degrees C centimeters per month. And so trying to figure out what that means. One way to think about this one of the nice things about these stochastic systems is you can solve everything exactly. And these systems can be completely determined by three quantities. One is how the damping brings you back to the steady state, and that is a time scale, units of 1 over time. There is a diffusion time scale, which is spreading things out. And then there's the angular momentum, which is a diffusive rotation time scale. It's diffusive, it goes both ways, but it has a preference. And so this angular momentum lets us say that these models do a pretty good job of capturing the dynamics, that we can use these models, simple models, to understand what's happening in these phase space, in these preferred patterns of oscillation. And so, to summarize, these are great systems to look at because we get to use all the buzzwords: complex, multi-scale, self-organizing, non-equilibrium. I don't think I've left any out. There's been a lot of work in the physics community about non-equilibrium steady states, and some of these ideas are proving to be useful. There's some interesting and fruitful interactions. This phase space momentum provides a quantitative metric for analyzing non-equilibrium spatiotemporal patterns of natural variability. We can compare data, and the question I want to pose is this broadly applicable to the kinds of systems that the community at this meeting is interested in? So thank you for your time.
Probability angular momentum, is it supposed to give you a clue about causality in your system?
No. In some sense, this is a diagnostic, and in the perspective from the climate system, is that this is something you use to talk about what's happening in the data or in models. In the sense, it tells you about mechanisms in that you can use this to test models. So if you had a dynamical model that you wanted to say, okay, I think this is what's going on in El Nino, and I build the model, and I ask, well, are these El Ninos right? One way to answer that question is to calculate the angular momentum and see if you get the right angular momentum.
So one interesting question about these types of models is how they would change with, say, different CO2 concentrations. So is there any way to guess how the different parameters because it seems like you did some fit to match the data, how would those parameters then change under different forcings?
So there's different ways to construct different models. The particular models I talked about were purely empirical models. They were just pure fits to the data. And so the question of how do they change as you do, say, climate change, that's a tough problem from this perspective. You'd have to do some other things. Maybe you'd do these fits to of different numerical models where you do have those knobs. So that's a good question, and it's something we're thinking about. We don't have any real answers yet.
So as we speak, I know lots of people who are taking these huge data sets of models right now and labeling them like crazy, saying, well, this oscillation's here, this oscillation's there, and then they're applying convolution neural networks and things like that to it. Where do you think that's going to go? Can you predict the future on that?
I think that's interesting. I think that, in some sense, it depends on how well you think these AI techniques really match human intelligence. These patterns that we're talking about, the sense that these indices are created by human experts who have, years to decades of experience looking at data sets and saying, I see this. I see this phenomenon. Gilbert Walker said, I see this oscillation. And, the magnetic wreaths that I mentioned and that Ben has worked on, that's something that they looked at the data and said, oh, look, I see this thing that's interesting. And to the extent that mechanical systems, computational systems can pick out things that humans find interesting, then it will be successful. And I don't know where we are. Someday, yes. I don't know the time scale for that.
I have a kind of a two-part question. One is, if you had an oscillation and it was an example of an equilibrium kind of thing, then what would the distribution of angular momentum look like? Because you showed
it would be symmetric.
Okay, and then the second
the mean
one
would be 0.
Second part then is, do you know if any of these oscillations you listed are non-equilibrium?
Well, the fact that they're asymmetric says that they're not.
Well, that was just two. I mean, do you know of any others?
You could construct one. You could imagine a pendulum with stochastic noise that would, imagine a single pendulum connected to a heat bath. That would be an equilibrium fluctuating system, and it would give you a symmetric PDF. You could probably calculate that analytically, but we haven't done that.
Okay, so I have one final question, if I may.
Okay.
So you mentioned linear response theory.
Yes.
And so to what extent has fluctuation dissipation theorems been proved for these non-equilibrium systems like the climate?
There's a lot of work on fluctuation dissipation theory in non-equilibrium systems, and I could not give you a brief review.
Okay, but people are actively...
Yes, I mean, it's sort of an obvious question, right? There's lots of people working on it.
Okay, thank you.
And I wish I could give you a better answer.
Okay, thanks.
So we haven't made use of those things in this
So you don't
particular...
need, because you skipped over the method, you don't need any kind of linear...
No, I mean, it's probably, you could say that might be one of the motivating assumptions for why you would pick a linear additive noise model.
Yeah.
But, it's a motivating assumption more than a piece of the analysis.
Okay, thank you.
Sure.
Let's thank Jeff again.
Okay, our next speaker is Yochai Kaspi from the Weizmann Institute. He will be talking about evidence from Juno mission that Jupiter's zonal jets extend down to the depth of the magnetic dissipation.
Turn off on HDMI here or just... I'll use this. Are you on that computer? Yeah, well, I'll switch. Okay. Oh, you're on yours, yeah. No, he's on his own. Okay. Sure. Yeah, good. Okay. As you can see, the title has changed since we sent the abstract, and the reason is that we split this talk into two. So I'm going to talk about how we can use the Juno gravity measurements in order to study or to confine the flow on Jupiter, the deep flow. And then in the afternoon, Keren Dewar will talk about how we can also use the magnetic field measurements in order to further constrain the flow. Okay, so we're going to combine these two measurements together. And this is work that we've been doing for quite a long time, maybe for the past decade, a group of us on the Juno science team. And finally, in the last 2 years, we have the data from Juno, and we can talk about how we can use the gravity measurements in order to confine the flow beneath this beautiful cloud layer of Jupiter. So to put us in the right scales, this is our little tiny Earth, and you can see that this is indeed a giant planet. Despite its size, as you know, it rotates really fast, so just under 10 hours. So it's a very ideal geophysical fluid dynamic systems in terms of the fact that rotation is really dominant. It also has very strong, large oblateness, so I'll get back to this point later on. Much bigger than Earth, so it has this flattening at the surface. You can see here at the the equator. You can see here the very strong zonal jets, the superrotation here at the equator, and then if we just kind of plot the more classical plot of zonal wind versus latitude, then you can see here about 6 jets in each hemisphere. And as I mentioned, the superrotation over here and this strong jet here. And also notice that there's a strong asymmetry between the northern hemisphere and the southern hemisphere, and I'll get back to that in a few minutes. Okay, and these jets or these patterns have been observed for really a long time. This goes back to the time of Cassini, back 350 years ago or so, and you can see even back then with the first telescopes, you can already see these bands on Jupiter and the Great Red Spot, and I'm sure many of you have already saw these kind of pictures before, so I'm not going to talk about that too much here. And basically, most of the observations that we had were just from the cloud level. Observing this cloud level, we had only one single observation beneath the cloud layer, direct observation. This is from the Galileo probe back in '95, and this is this measurement that the probe dropped in somewhere around latitude 6 near the equator. The velocity there, the zonal wind velocity, was 80 meters per second, then went up to 160 or so, and then remained constant until the probe was lost at 22 bars. Okay, but that's one measurement at one time at one location. Okay, so how much can that tell us about the global circulation of Jupiter? Not much, but still, it's an interesting measurement, the fact that the flow remained constant for such pretty deep, although 20 bars is about 130 kilometers compared to the 70,000 kilometers radius of the whole gas giant. But we should remember this and keep this in mind. Now, beneath the cloud layer, we have, of course, no direct measurement, but you have some ideas for modeling and people working on the interior. And basically, there's a dynamical atmosphere, which prior to Juno, we did not know how deep it is. Then there's a layer of metallic or molecular hydrogen down to about 10% of the radius. Then it becomes so dense, so from pressure ionization, it becomes ionized down here. And then maybe or not, there's a core, and this is a big question. People doing internal models can get solutions for Jupiter with and without a solid core in the interior, and this is also one of the big goals of the Juno mission. And this is really where Juno comes in. The goal of Juno is to look beneath the cloud layer, like all previous observations, and try to understand what's happening in the interior of Jupiter, both in terms of dynamics, which is going to be what I'm going to be focusing about, but also in terms of the core and the internal structure. Okay, so Juno was launched in 2011. Went in this orbit where it went back to Earth for a flyby in 2013, and then spent 3 years in cruise to Jupiter and arriving there 2 summers ago, and since then has been in orbit around Jupiter. And the orbit has been a special orbit, so every 53 days, Juno goes around Jupiter in this very eccentric orbit. So at the closest approach at perigeo, it's about 4,000 kilometers above the cloud level. This is much, much closer than any other spacecraft in history. And in terms of what we're trying to do, which is get a very good gravity measurement for studying the winds, and I'll elaborate on that later, then, of course, the closer we are, the more accurate gravity measurement we can get. And this is one of the main reasons for having this very eccentric orbit going around. So far, there's been 15 orbits of Jupiter. The last one was just last Friday, and they've all been very successful for all instrument, not just the gravity experiment, which is what I'm going to be talking about today. And let's now pretend that we're riding on Juno. Okay, so this is a picture of Jupiter. This is the pole. The obliquity is very small, so the pole is roughly where the terminator is. And now this movie takes you on a 2-hour journey from the North Pole to the South Pole. You can see the vortices here close to the pole. And as you get closer and closer here into lower latitudes, you can see more jets than vortices. These are latitudes and approaching the equator. Around here, a lot of detail, a lot of structure, all the turbulence over here. This is the equator, more or less. The red spot passing, that's 282 south, and then coming out from the South Pole. Really a beautiful, almost looks unreal, I think, kind of artwork. This is nature. It's not artwork. Anyway, so Juno is doing this every 53 days, and the orbits are set in such a way that we're going over different longitudes every time. So we're building kind of a 3D picture of Jupiter, and there's also a latitudinal drift of perigeo of about 1 degree per orbit. Okay, so we're now, the last perigeo was about at latitude 22. This is a mosaic putting a bunch of these together. You can see the structure near the poles. This is the pole over here, and you can see these vortices around the pole. Even a better picture of that just came out this year in this paper, showing from the infrared instrument. You can see this is the North Pole, so there are about 8 vortices around the pole that you can see over here. In the South Pole, there are 5 vortices that you can see over here. This is latitude 80. Okay, so the size of these is roughly 4,000 kilometers in diameter. Okay, but I want to go now and focus about how deep are these zonal flows. And again, this is an image that I'm sure you all saw before. This is kind of the iconic set of images from Voyager almost 40 years ago. And you can see here the superrotation again, and all this structure and all these multiple jets that we have in each one of these hemispheres. And this has kind of been a big question ever since. People looking at these pictures, are we just looking at a surface layer of clouds, and that's what you're just seeing, just kind of a weather layer? Or are these zonal flows something which is embedded very, very deep into the planet? And we already saw this week a few talks relating to that. And there's been kind of two camps on this, kind of one coming more from the atmospheric community, where, as we know, if you have a rapidly rotating planet, then what we get is, because of PV arguments, you get flows along latitudes. These are these zonal jets, and occasionally you will get some vortices in between those. And there's been many papers showing that even if you just simply take an Earth model and just make it more rapidly rotate, then you will get these kind of multiple zonal jets. But typically, these ones do not give you superrotation at the equator unless you do something special. And people have shown before that you can do various things to get superrotation as well. Now, the other approach, which we have saw also this week, is coming more from the dynamo community or from the solar community. These kind of models of deep convective models, where if you have a hot interior and have convection, which is typically aligned with the axis of rotation, then there's been various ideas of how these convective columns can interact to give these east-west jets that we see in these kind of movies. Okay, and this has been an open question and heavily debated in the literature. I think now Juno can at least provide us some more insight about what's going on. Are these flows shallow or are they deep? Okay, so that's what I'm going to be doing for the next few minutes, explaining how we can do that. And the idea is that if we have a close-flying spacecraft that can measure the gravity field very accurately, then if these flows are deep enough, then they can provide a big enough perturbation to the gravity field so that we can actually determine, at least if we have kind of this kind of a scenario or this kind of a scenario, and maybe even more, we can even now confine the vertical profile of these flows. So just to give you an example, this is the percent of total radius versus the percent of total mass. Okay, so if you just go in 1% into Jupiter, then it's roughly 0.01% of the total mass. But if you go deeper, for example, if you go 4% in depth, then you already have 1% of the total mass of the planet. So unlike, say, Earth's atmosphere, which is just 1/1,000,000th or less % of the mass of the total system, on Jupiter, the atmosphere, depends how you define it, but let's define it here as how deep these flows are going. It can contain a significant % of the mass of the planet, and therefore came up this idea of measuring the gravity field and look if that can affect, that can be allowed to measure the flows. So how do you measure the gravity field typically? You look at these gravity harmonics. So these are J sub n's, which are just how the density is projected on these Legendre polynomials, these P of n's over here. And this density can be split into two parts, one coming from the static planet. So what I mean by this is assume that there's no dynamics. It's rotating as a solid body. So these are these rose bars here. And then in addition, they might have some variation due to the dynamics, and that's these rho primes over here. So all the dynamics are folded into these variations. Now if you just look at the static component, then you get these, this is kind of the spectrum. This is J sub n as a function of the gravity degree. Before Juno, we had J2, J4, J6. These were the measurements. And this is a model by Bill Hubbard, which is in many ways kind of the father of this whole experiment. He's been advocated for this experiment for many, many years, and it was finally done under his leadership and idea. And you can see that these things are decaying as a function of zonal gravity degree, and you can get some intuition for that if you just think about the shape of these polynomials. So of course, J2 or P2 has this kind of big belly at the equator, and of course the biggest deviation from sphericity comes from this oblateness at the equator. So of course J2, this is a log scale, so it has a much bigger signature than J4, J6, etc. J4 has this kind of shape, so also has some kind of equatorial bulge, and that gives you that, and then you can kind of imagine why these would decay for more complex functions. Note that all the odd ones here are just absolutely zero, and the reason is that if you have a static planet, then it should not, and it's a gas giant, it has no asymmetry between north and south, right? It's just kind of just a rapidly rotating ball of gas. North-south should be symmetric, and therefore these harmonics are completely, are just zero. Of course, any asymmetry would say J3. All the odd harmonics, I mean, are zero. Any asymmetry here, this is J3. You can see this is asymmetric between north and south, and therefore you don't have that kind of an effect. Now, if you take a GCM simulation, kind of the one that we saw earlier this week, and you just put that in this machinery and calculate what's going to be the gravity harmonics, then you get this kind of a structure. So you can see that beyond J10 or so, then the gravity anomalies or the effect of dynamics becomes bigger than the static component. Okay, so here came the idea by Hubbard saying that if we have a close flying spacecraft that can measure J2, J10, 12, 14, etc., maybe we can separate between a static planet and one that has dynamic on top. Now note that the GCM simulations have kind of the seesaw effect, and the reason is that the simulations are not completely asymmetric between north and south, and therefore you get some effect from J3, J5, and these higher harmonics. Then another idea would be to, if you can measure J3, J5, J7, then that can give a signature about the asymmetries in the system. Now, if we look at the wind themselves, so here I'm plotting the wind that we saw before on top of kind of a picture of the planet. The wind, as we mentioned before, are not symmetric between north and south, okay? So if we can measure, this is what we've been advocating for in the last few years, if we can even measure these ones, then that will give us a pure signature of dynamics, because we're not competing here with a static component. This is just a signature of the dynamics themselves. Okay, so that's the idea behind this experiment. And I can skip this. And the idea is that, well, this is just one GCM. The planet doesn't necessarily look like the dynamics of this thing. So what we really need is some kind of dynamical model which will allow us to relate between the fluctuations because of the flow and the gravity field. So in a way, we want to systematically vary the atmospheric depth of the flow and see what's going to be the gravity signature of that. So we need the relation between the flow, the density, and gravity. So of course, if you want to go from density to gravity, it's just this. You just integrate the density to get the gravity. But to relate the flow and the density, what we can do, and what we do use, is just basically thermal wind balance. Okay? So this is a large rotating object. We expect it to be to leading order, geostrophic, and therefore thermal wind should hold. So if you take whatever velocity field you want to put in, you can calculate the density anomalies and then integrate that to density and get the gravity fields. This is kind of the relation that we're doing between flow and gravity. Now, the simplest model that you can imagine doing that is just take what you know, right? So what we know is the zonal flows at the surface, right? But we don't know how these extend into the interior. So what we do is we assume the simplest model possible. So take the surface flows, then extend them into the interior with some kind of exponential decay function. Right? So with this exponential decay function, we have a deep flow profile. It can be looking like this or like this. If say if this parameter h is very deep, then you get these kind of flow along cylinders. And I'm not going into explaining why we're assuming this kind of flow along cylinders. I'll be happy to talk about that later. And if the h is very small, then the flow would be decaying towards the interior. Then we use thermal wind to calculate the density profile. And then what you can get is the gravity anomalies, but now as function of depth. Okay, so the deeper the flow, more mass is involved, and therefore the deeper anomalies you're going to have here. So these are, for example, if the flow is 10,000 kilometers deep, then we get this kind of signature. If the flow is 100 kilometers deep, then you get this kind of signature. On this plot, solid means positive number because this is a log plot, and open means a negative number. Okay, so just notice, for example, if you look at J10, that even if the flow is very deep, we're still not bigger than the solid body component, so it's going to be hard to separate between the two. But if you look at J3, then even a very shallow flow, order of what we saw from Galileo, is still giving you a signature which is bigger than the Juno sensitivity. Okay, so this is kind of what we were aiming for in these measurements. And so this is the prediction for, from 5 years ago. And the measurements came, this is from 2017. We had since 5 measurements repeating exactly the same measurement. And what you see here, so of course the solid body numbers are what one would expect and have been some of them measured before. But also, most importantly, look at the odd values. The odd values are very big, much bigger than the sensitivity. See, 3 of them are negative, one is positive, and very big numbers. So even from here, you can basically see that the flow depth is somewhere between 1,000 and 3,000 kilometers. Very deep, much deep beneath the cloud level. A different way of looking at the same plot is just plotting separately J3, 5, 7, and 9 as function of depth. Okay, so this is kind of a theoretical expectation. And then you can put on top of that the measurement. They have the 4, and these are 4 independent measurements for J3, 3, 5, 7, and 9. You can see that all of them cross the theoretical measurement roughly at the same place, somewhere between 1 and 3,000 kilometers. Okay, so this is kind of an indication. It's not just one single measurement. It's 4 different measurements giving us all the same indication that the flow is really deep, reaching these kind of levels. You can see that not like J5 example doesn't exactly cross the blue line. And this is because this is a very simple model, just one kind of simple exponential decay. We don't know that the flow is decaying exponentially. So then we went and did more sophisticated things, which I don't have time to elaborate on, but I'll just tell you that the best fit that fits all 4 measurements within 3 sigma is this kind of flow profile. Okay, so this is the surface where the cloud level is, and this is the depth. This is in kilometers. This is in pressure. Okay, so notice this is like 3,000 kilometers is roughly 100,000 bars in pressure, a very, very deep atmosphere. This is the flow profile with depth. If you integrate the density down to 100,000 bars, you're talking about 1% of Jupiter's mass. Okay, so think back about those movies and ask yourself, so what's rotating? It's 1% of the mass of the planet is kind of rotating around in these bands, these east-west bands. A huge atmosphere, that would be 4 orders of magnitude thicker than the atmosphere of Earth compared to its size. A very, very thick atmosphere. Now, these results imply not only that we know the depth, but that the meridional structure of the winds is the same from what we see at the surface goes into the interior. So you can ask yourself, well, maybe it's just a coincidence. Maybe if we had a different flow profile, we can still match all 4 numbers over here. So as a test, what we do here is we take the winds of Jupiter, but now put some random profiles. So we took thousands of random wind profiles on the surface and do the same kind of experiment. Try and see, can we get a match to the data? This is a summary of those results. So each dot here is a solution along the same lines I described before in the plane of J3, J5, J3, J7, etc. So each one of these blue dots is a random wind profile. The red is the measurement and its uncertainty ellipse that you see over here. And the black is taking the specific profile from Jupiter's surface. Okay, taking that profile and extending that into the interior. And you can see that that is better than 99% of the cases. Okay, so it seems that it's going to be very statistically unlikely that there will be a different meridional profile beneath the cloud layer. Now, what else one can do is say, well, we don't know that the same vertical profile has to continue in every latitude. So we can release that kind of constraint. And then what the solution that we get is this is going to be the vertical profile. And this is where this middle point varies with latitude. So you get deeper flows near the equator and less and kind of shallower flows close to the pole. But one needs to be careful here because we have only 4 measurements. And if we release the degrees of freedom to be infinite, we can get all kinds of solution and kind of all kinds of wiggles here and very specific profiles, but that won't mean much. So we need to be somewhat conservative, and we're not releasing too much the degrees of freedom to get more varied solutions. So this is kind of just to give a sense what will be the best fit solution if one releases this kind of a constraint. But I think the bottom line from this, regardless of what the exact profile is that to get any kind of match to the gravity data, the flow has to be very deep, and this order of magnitude of 2,000-3,000 kilometers is a robust result. Otherwise, you would not be able to match the gravity data in any kind of way. Okay, so 3,000 kilometers deep. Now I keep saying how deep it is and how deep it is. From atmospheric scientists' point of view, this is really deep, right? 3,000 kilometers, 1% of the mass, 100,000 bar atmosphere, that's really deep. But from the planetary perspective, well, look, it's still just a shallow layer compared to the 70,000 kilometers, or if you think back on kind of the Busa picture, that's very different from what we're seeing over here. I don't have time to show more about why, but if you look at the even gravity moments, you can basically show that there are no deep internal flows in this region. Okay, so everything should be pretty static in this region, or very, very weak, order, say, 1 meter per second, but not more than that. And the core is still an open question, working on it, many groups around the world. But what it seems is that the core is not like a solid core that you would expect in the classical picture, but more of a fuzzy core that kind of dissolves into the metallic hydrogen around it. 2 minutes about Saturn. Saturn, there was an equivalent experiment on Saturn done last year by the Cassini grand finale, what's called. So the last orbits of Cassini kind of drop between the planet and the rings. And what they measured is a profile or a gravity spectrum like this. I'm not going to go into too much detail here. But just notice that the odd harmonics that we used easily with Jupiter, because they were very big, are not much above the uncertainty level. But notice that J8 and J10 are really big, much, much bigger than the solid body component. And the only way you can get a solution to that is to have very, very deep flows. Let me skip this, but just say that the vertical extent of these flows has to be about 9,000 kilometers deep, so 3 times deeper than on Jupiter. If you compare Jupiter and Saturn, okay, so this is the depth of the flow on Jupiter, and this is the depth on Saturn. You can see that the flow on Saturn reaches much deeper. But this is very important. Notice that the electric conductivity profile that's expected kind of goes up right around the same region, both on Jupiter and on Saturn. So this has actually been predicted before by MHD arguments. People like this paper by HAO and Stevenson from a year ago, showing that, or suggesting that because of the ohmic dissipation, because of the effect of the Lorentz force at depth, that can act to damp down the flow and act as a kind of basically a friction layer down below. And you can see how consistent both results of Jupiter and Saturn are with the depth where this is expected to grow. And if we take the flow that we found for both planets, you can see how that seems to look in this kind of plane. So Karen this afternoon will basically pick up from this point and talk about how we can use the magnetic field measurements, which I haven't talked about yet, in order to further constrain the flow in these regions down here where the electric conductivity picks up. Okay, thank you.
So very nice analysis, but I do have a question about the assumption of separability, assuming that there's something magic about the zonal velocity as a function of latitude at the weather layer where we see it, which is about 980 millibar. Okay, so there's the region below, right, is quite different than the region above, say, the tropopause and the top. But if you look at the lower stratosphere and you look at the upper troposphere, you got lots of infrared measurements between about 1 millibar and about 570 millibar. And so you can use the thermal wind equation there. And you can also tie it, in fact, to some direct observations from the Cassini probe at 6 degrees north. And you see that it's all over the map, that when you go up and down in the atmosphere, it does not look like the usual velocities that you show from the cloud layers. And so there's no separable model or even slightly more complicated model between the radius and then the latitudinal dependence. So it's that certainly can't make that separation near the tropopause. So I'm just wondering how dangerous assumption it may be to go down below. Now, granted, there's different physics there, but it's a big assumption.
Yeah, that's a good point. Well, remember that everything that happens above the cloud layer to the levels that you described in the troposphere and stratosphere, there's a very low mass in there. So whatever variation you're going to have there, that will have zero effect whatsoever on the gravity measurement, because we're talking here about we need mass, so you need to go deep. So yeah, it's possible that beneath the cloud level you have a completely different structure, and that would. But as I showed you, the gravity measurements. You can say it may be a coincidence, but this is a prediction to what's going to be the gravity signature as a function of depth, given the flow profile that we have at the cloud level. And then you get 4 measurements, which, bam, give you the right sign and the right numbers. So, and then I'll also show you this test that we did with varying the profile. So possibly that there's a profile underneath, but if you want to invoke that, you need to come with a mechanism or some explanation to why the flow profile will be different. If you have a different profile, you need to have some variation because of thermal wind, a variation of the temperature profile at depth, or something like that. The variation that you were talking about, high above, don't really affect this because there's just no mass. So the gravity is not at all sensitive to whatever you have up there.
Any more questions? I have a question. You said it was better than 99% of the other. Did you actually have a look at the ones that did better and saw if they were at all reasonable? The 1% that did better than your...
Yeah, so these are the green ones over here. They were pretty randomly spread over here. The problem here is that you're projecting the winds along cylinders, but you're looking at spherical harmonics. Yeah, so you can have a very small change in the width of the winds, and you will project differently on the harmonics. Yeah.
Okay.
So these J measurements that you're taking, they're spherical harmonics, of course, in the horizontal direction, but they don't form an orthogonal set in the radial direction. So in fact, the measurements that you make are rather correlated with each other. If I put a perturbation somewhere inside Jupiter, I'm going to affect all of them. So how significant should I take the fact that you get a model that when I put a perturbation in, I get bango for all 4 of them? How well correlated are those measurements?
No, they're not correlated. They're separate measurements. It's right that if you look at the correlation function, it's not completely diagonal. You have some cross correlation terms, but these are not big compared to the diagonal terms. So you're right. Technically, it's not completely decorrelated, but there's not a very strong correlation between them. I'll add also that if you take this wind profile and this also has a signature in the even harmonics, right? So the signature you get for J6, J8, J10, which is not independent, you can't separate, you need to separate that from the contribution of the solid body, but if you subtract that, that also gives you the right sign and the right magnitude. So it's not just these 4 measurements, but actually 7 measurements that contribute to the same thing.
So it's very interesting that you go deep, but not right the way through, the way Busse would have pictured it. Yeah. So what do you think's going on here?
So that's exactly the issue with the magnetic field. As I showed you, the electric conductivity, which is a function of the pressure and how deep you go, picks up right around this region. So, and this has been suggested even before. It goes back to suggestion by paper by Liu in 2008, showing that ohmic dissipation should act to dissipate the flow at these levels. Okay, so the picture that you have in mind is, and again, I didn't have time to show it here. Think about ferrocell dynamics. Okay, so you have eddy forcing on top, the Reynolds stressing are forcing the flow. Then the flow continues into the interior. But then instead of Earth ferrocell dynamic, where you have friction from the surface, you now have friction from the magnetic field, which is damping down the flow at that depth.
The magnetic field is, we'll hear more about that later, I guess. So the configuration of the field, is then that surprising, or? We'll hear about
We'll hear
that
later. So the field, you're talking about the spatial variation in the field, or the vertical variation?
The vertical variation.
Well, no, it's not surprising. These measurements are pre-Juno, so this is like theoretical measurements for how deep that would be.
I just wanted to comment about this point because actually, if you have higher conductivity, which means that more energy of flow can transform into magnetic field because magnetic field is more frozen in the flow. Then, when electric conductivity is higher, then flow should decay not due to ohmic diffusion, but transform energy to magnetic field. This is another possibility.
Okay, perhaps this is not even the fully conductive. This is not the metallic hydrogen region, which will be way down here. This is the semiconductor region. So I'm just referring to the fact that this is the place where magnetic field begins to play any kind of role. Like above that, it has basically no contribution in this kind of vorticity balance.
Okay, let's thank Yochai again.
Oh, yeah.
Okay, our final talk before coffee is from somebody who I recognise from earlier in the conference, Mikhail Sabat, who's going to be telling us about inertial instabilities and rotating fluids and a little bit about turbulence.
Yeah, so it's me again. Takes time. Okay, so as I told you yesterday, I'm replacing Benjamin Favier, who could not make it. So this talk is going to be the follow-up of the talk I gave yesterday, but this time I'm going to talk about a local model on the turbulence, so the saturation of those inertial instabilities. So this work was initiated in a collaboration with Adrian Barker from Leeds. And as usual, the one who really made the work is the PhD student, Thomas Lerin. So for those who were not here yesterday or who fell asleep at some point, we are interested in inertial instabilities, meaning instabilities driven in planetary core by some harmonic excitation, resonantly exciting inertial modes, which are the eigenmodes of any rotating system. So those excitations are either libration, precession, and tides. They are very tiny amplitude. And then we have built some experiments to look at the flow generated. So you see that you excite waves from those tiny perturbations, which grows and grows in amplitude until it saturates and gives rise to turbulent flow. So what I showed yesterday is that the mechanism is well known. The threshold is also well known. The mechanism is a parametric resonance of the base flow with two waves. And once the forcing amplitude is larger than dissipation, well, the instability grows. We can extrapolate towards planetary value, and those instabilities indeed apply to planets. And finally, those instabilities are dynamo capable. They are capable of sustaining a magnetic field. And we have shown this using direct numerical simulation in an ellipsoidal container. But there are still questions remaining. And the one I will address today is how does the flow saturate? What is the turbulence that is excited by those inertial instabilities? So the first thing we have done to answer this question is to push both our DNS and our experiments to the most extreme turbulent cases. So here are some pictures from the tide experiment for the libration experiment and numerical simulation using direct numerical using NEC 5000. And those are spectrums, so temporal spectrum, the frequency and the power spectrum. In red, it's a direct numerical simulation. In blue, the lab for the tides for the libration. So don't care too much about this. I just put it for Steve, because I know he likes feeling like this. What is interesting here is that you have a lot of energy up to a cutoff frequency of 2. Same for here. The two cases are very similar, so the instability is really generic. And you have a lot of energy here. You see some peaks, and you have energy down to very low frequencies. These two here correspond to the threshold for inertial waves. You only have inertial waves below a frequency of 2. The big peak here is the forcing. Each time we force at 4, we first excite the instability with a resonance at 2, as I've shown in my movie several times. But then we have energy all the way from 2 to 0. And indeed, if you think about it, you might imagine two ways to saturate your flow. So again, we start from a base flow coupled with two inertial waves. We get the instability. And then we can imagine two routes, if you want. The first one is like in classical turbulent, rotating turbulence. You will have nonlinear interaction in viscous boundary layers that will generate geostrophic flows. You might also have quasi-resonant triads of your waves with 2D modes that will also generate geostrophic zonal flows. So we have already seen that. We get flows which are mostly invariant along the axis of rotation. But another way also is a cascade of triadic resonance. Indeed, once you have excited inertial mode, you may expect each mode to itself resonate and give rise to two additional modes, and so on and so on. So in that case, you will generate a fully 3D flow with no preferred orientation along the axis of rotation. And if you look at direct numerical simulation and our experiments, you might indeed see those two trends. So if you look at these experiments, which is the libration experiments but in inner core, you will see more geostrophic-like structure in the outer cylinder and more wavy structure in the inside the tangent cylinder. Here are two numerical simulations. So those are spectrograms. So it's the time, the frequency, and the color scale is the power spectrum. You see the excitation is at 4. So that's for 2 Ekman number. So at large Ekman number, you have the excitation and just one additional frequency corresponding to those two modes that are excited and that saturate. But when you go to smaller Ekman number, you have the forcing, the first resonant mode, and then you have a cascade of different modes appearing. But you also have a lot of energy around 0. So this is already interesting, but the problem is that we are not sure it's realistic for planetary application. Indeed, DNS and experiments are at rather large Ekman number and rather large forcing amplitude. This is okay to study the threshold because, as I showed yesterday, we can compensate the fact that we have lots of, we are more viscous in the lab and DNS by forcing harder the amplitude of the excitation because only the ratio between the two does matter for the threshold. But when you look at the nonlinear saturation, it's not the case anymore. And indeed, what we need is really go to the planetary limit, which is very small forcing. It's 10 to the minus 7 in the Earth core, for instance, and very small Ekman number. So it's 10 to the minus 15, for instance, in the Earth core. So to do that, we have used a tool, which is a usual tool in astrophysics, but it is not in geoscience. So we use a local model. So the code Snoopy developed by Geoffrey Le Sur, and which is adapted in this case to mimic tidal flow. So this is a shearing box model, so it's usually used for accretion disk, but here we have a base flow that does that, which is like, actually it's more like that, base flow, which mimics tidal forcing. And then we solve the dynamics excited by this base flow in a cube, which is like a small part of my core. And then we can use very fast method and push the parameters to the limit. So go to 510 to the minus 3, which is way smaller than what we can do in the lab and global simulation. And we can start saying that this is small, not as small as in planet, but already much smaller than 1. And the Ekman number 10 to the minus 7, which is 2 orders of magnitude better than the lab. OK, so we have run some first simulation that I show here. Those are 3 pictures corresponding to those 3 times. And here, it's the kinetic energy as a function of time. In black, it's the total energy. In blue, it's the geostrophic energy. And in red, the non-geostrophic energy. So what do we see here? We have first an exponential growth, which fits well with the model. This is this picture. And then we have the first part of saturation, where you see that the total is about, the non-geostrophic and geostrophic part are about equal. This corresponds to this. So you see in the nonlinear saturation, you begin to build those geostrophic columns, but you still have wavy motion all around here. And finally, you have a second part for the saturation, and actually this corresponds to an inverse cascade, because these quasi-2D structures have an inverse cascade that finally builds up a large-scale vortex. Okay, so that was already seen before by Adrian Barker a few years ago. Another way to show this is to use a projection of the spectrum following what Yarom and Charlotte did in their paper in 2014. So to see the wavy part of the energy against the non-wavy part of the geostrophic part of the energy, we can actually project the spectrum, the power spectrum, into a angle frequency domain. You remember that inertial waves have dispersion relation that write like this. So the frequency is 2 times the angle that the wave vector makes with the vertical. So if we take our power spectrum and we put here the angle of the wave vector and the frequency, the dotted line here corresponds to the cosine. So if you have energy in waves, it should align with this theoretical line. Okay? So those 3 spectrum correspond to the 3 times here. During the initial time, we have an exponential growth. So the forcing is at 3 in that case, sorry. And we only have energy right here because we are only coupling 2 waves with a frequency half the forcing each. Then first saturation, we begin to have energy spreading actually because you have an advection of the initial excitation. And finally, in the final time, you have energy almost everywhere and no focus at all around the dispersion radiation of inertial waves. So we are really in the geostrophic saturation limit. But we think that one ingredient is missing in this because we are in a periodic box, triply periodic box. And if you build geostrophic modes in the core, they will end up touching the boundaries where they will dissipate. Actually, we will have Ekman pumping, and this can be computed easily, where you have a square root of Ekman number here, and the ratio between the size of your column, which is the size of our box in our case, divided by the depth. So if you go in the core, it will be the whole depth of the core. So you have an aspect ratio that appears here. So in our model, we can add an additional friction term only on geostrophic mode that scale like this, minus the square root of Ekman, the aspect ratio of our box, times the velocity. And in that case, the dynamics change completely. So here, initially it's the same, so we are growing the instability. Then we have this slight overshoot, and then the nonlinear saturation. Actually, we never see the formation of geostrophic structure, but we stay in this state, which is actually, I will show you, inertial wave turbulence, where we have 3D structure, waves, weakly non-linearly interacting and saturating like this. So of course we have a free parameter here, so we must check that it is not our results does not depend only on this parameter. So we have tested various values. Again, this parameter would correspond to the aspect ratio of our box compared to the full depth of the tank, of the core. So this is for the reference case, and here for including the Ekman pumping for a very tiny and a larger coefficient. But in both cases, what we see is that the geostrophic component is at saturation is way smaller than the non-geostrophic component. And if I use the trick of projecting onto this angle frequency domain, most of the energy seems to align along the axis, along the curve showing the dispersion radiation of inertial wave. So that's completely different from the first case here. And if we push even harder, so this is the most extreme case we were able to make for beta 5 10 to the minus 3 and Ekman 10 to the minus 7. You see it's very convincing. We have only energy in the dispersion radiation. If you look at the frequency, a cutoff of the power spectrum in the frequency, you have the strong cut at a frequency of 2 again. We only have energy in inertial waves, and we also have lots of energy at the low frequency. The last key point, if we compute the Rossby number at each scale, it's the scale here, k, and the Rossby number, we are always around 10 to the minus 1. So we only have weak interaction. So we have weak interaction and energy only on inertial waves, meaning that we have strong signature of inertial wave turbulence. Okay, so what happens in planets? So the key ingredient to know where we go is really this ratio between this ratio between the geostrophic velocity and the 3D velocity that we can get. So to have ideas about that in real ellipsoidal system, so we have made experiments for the geostrophic component. So it's the same setup, the tidal setup in that case as before, except that we force at a given frequency where we do not have the instability. So we make only a direct resonance of one wave, and then we look at the flow. So one wave non-linearly self-interact and generate geostrophic flows that you see here in a vertical cross-section. And this is an horizontal cross-section where we measure the velocity using PIV, and you see we have strong jets, so strong geostrophic jets like this. So we have made these experiments varying the amplitude of the forcing, and we have a nice beta square, which can be expected because, again, the geostrophic flow comes from nonlinear interaction of the waves, which are forced with an amplitude beta, so we get a beta square scaling. And also, interestingly, we have a dependence in Ekman number, which go, in that case, like Ekman to the minus 310. So we can safely say that the geostrophic velocity scales typically like beta square, Ekman to minus some exponent. In that particular case, is 310. In other case, we found other exponents, but they are always smaller than 1/2. And for the 3D mode, so the saturation of the 3D mode, Adrian made systematic studies using numerics, and he finds that it saturates like beta. So all that together, we can try to build a regime diagram. So in x-axis here, I have the Ekman number. Here I have the forcing amplitude. The instability threshold I showed you yesterday goes like beta Ekman 1/2, so it's this curve here. So below this curve, we are stable for the instability. Above this curve, we are unstable. And then I draw another line here, which is when, so this is the instability threshold. This is where the 3D mode is larger than the geostrophic mode, sorry, is larger than the 3D mode. So above this line, we expect geostrophic turbulence. Below this line, we expect wave turbulence. Our experiments are right here, around 10 to the minus 5 in numerics, and the planets are around here. If you remember my slide yesterday, we have lots of planets very close to the threshold. So we expect in planets, at least in some planets, to have wave turbulence. So what we need now is a theoretical description of the temporal and spatial spectra associated to the inertial wave turbulence, which is not an easy task because those waves are strongly anisotropic. You remember the dispersion relation, where the frequency only depends on the angle of the wave vector, and there are no complete theoretical prediction for this right now. So again, we take a small parcel, we do numerical simulation in square box. If we have strong forcing, we go toward geostrophic saturation. If we have weak forcing, still unstable, we have a 3D inertial wave turbulence. So what we are trying to do right now is to do some numerical simulation, some experiments, sorry. So we have built a new experiment which is bigger so that we can reach larger Ekman number and which rotate faster. And you see it's a very beautiful, I'm very proud of it. Very beautiful experiment. So it's a libration experiment because it's easier to do in the lab. And we use a, you don't see it, but we use a trick. We already heard about it. It might be interesting for experimentalists. We use fluorescent PIV particles, meaning that we have a laser sheet in green, which lights particles, and those particles emit in orange. So it's very, very convenient in the lab because especially when you have an ellipsoidal container like this, you have reflection in all the direction and you don't see your particle very well. With this, on our camera, we put an orange filter and we only see our particles and no reflection at all from the laser direct. So we can do very nice PIV measurements. And those are the three first measurements we have done so far. So this is the amplitude of the forcing. And this is measurements of the mean flow. The threshold for instability is here. and we have two different behavior here. First behavior at large forcing, which have a strong geostrophic flow, a strong mean flow, and another one here that I will show after. So in this experiment, if we take a PIV measurement in the equatorial cross-section, this is what we see. So we form those big geostrophic zonal flows that I showed before. But interestingly, if we are in this domain, well, we don't see the zonal flow is almost zero, but what we see, this is a spectrum with various peaks, and if we filter out our PIV measurements at one peak, we see nice structures like this, which actually correspond to triadic resonance. So you see this mode coupled with this mode. The frequency is 0.56 here, 1.45 here. So if you add the two, it gives you a frequency of 2. So it's really a secondary resonance of the first, above the first mode that we have excited for the instability. Same for here. Yeah. 4 minutes. Okay. I just want to mention some last study rapidly because it has some relation with that Nick showed us. So since things were working well with rotating fluid, we did the same with stratified fluid. So we took a model of a planet which is stably stratified and non-rotating, but around which you have a moon which excites tides. Okay, so we have non-rotating, but we follow a parcel here of fluid, and because of the tidal excitation which is rotating around the planet, you have a small drift, so it's a Lagrangian trajectory in the fluid. It's exaggerated here, it's for very large tidal amplitude, but it's just to show you the motion. So if we follow particles through time, it does, you have a forcing like that because of the tide on the non-rotating fluid. This tidal forcing can also excite, now it's internal wave, because we are stably stratified. So we have done a flow K analysis and a DNS with Snoopy again, and I'm skipping all the details just to show you the saturation. So those are pictures of two cases. N is the Brun-Weissala frequency, the Reynolds number, and S is the axis, it's the angle between the direction of the stratification and the axis of rotation of the tide. So you see in those two saturations with the Y vorticity and the density anomaly. So we see a layer-wise structure, as often in stratified turbulence. But what is interesting, when we try to characterize this, so those are two spectrums. This is for the kinetic energy. This is for the density. We have a nice equipartition of energy between density fluctuation and velocity, and we have a nice -3 slope. And in that case, it's not just, we already think it's a -3 slope. Another key element is that if we separate the spectrum between layer-wise slow mode, so mode with a kz equals 0, and the other mode, almost, we see a mostly horizontal structure in this, but those purely horizontal structures have not so much energy. We have really 3D energy in our system, and if finally we project onto the same trick onto the angle frequency domain, you see that in the most extreme case, again, we have energy along the dispersion relation of internal wave. And the very last point, I stop there. If we look at the time spectrum, so in this case, you have a PSD, the frequency. The forcing excitation is here in that case. The Brun-Weissala frequency is here in that case. We have a very nice -2 slope for this turbulence, which looks like what is the classical -2 slope that is found by Garrett and Munk in the ocean. What is new here, you might have already seen that internal wave turbulence gives this -2 slope, but it was for a triadic resonance instability of wave excited by large-scale tidal flow on the bottom topography. What is new in our study is that it's really a bulk instability that appears inside the ocean without any topography, and that is excited by the tides themselves. And I just put my conclusion and let that here, just mentioning here, there's a very nice picture on Enceladus. So among the things that we would like to, where we would like to apply our results in terms of dissipation, for instance, is this nice small moons of Saturn, where you have a huge amount of energy, incredibly, which is abnormally high power going out of the planet. It's a moon of Saturn, it's close to Saturn, so it has a huge tidal dissipation, and you have those very nice features, those very nice jets going out of the crust. So showing that we have a lot of energy to dissipate, so we would like to see if our model of turbulence could apply to those subsurface ocean. I stop there. Thank you.
We have some time for questions.
Thanks. That was interesting. I wanted to ask about the part that you focused on, mostly the rotating experiments and what you were calling the wave turbulence regime, where it seemed to be quite three-dimensional and not in a columnar fashion. And you mentioned that the Rossby numbers were also quite small, a tenth or less. So that would sort of suggest that you know, if you're going to have sort of non-columnar behavior like that, then the thermal wind equation should apply. And so there's going to be horizontal variations of the thermal structure, temperature, or some buoyancy variable. So all of the dynamics of the velocity structure is going to be coupled to the dynamics of the buoyancy field. Mm-hmm. And maybe you said it and I just missed it, but like, what is the source of the buoyancy in this case? Do you have convection going on, or you need buoyancy variations in order to sort of explain the velocity patterns that you showed at small Rossby number?
So in all our models for now, we do not look at buoyancy in the rotating case. We have done the rotating case and the stratified case, but separately. So one thing we need to do is to do both at the same time. So that's the first part of my answer. Then in planets, of course, you are I
think what I mean, though, is that your results demand, they can't be constant density or you wouldn't get that behavior, I wouldn't think. I mean, you know, if
thermal wind assumes no time variation or slow time variation.
Well, if the Rossby number is small, if the Rossby number, if there's huge time variation, the Rossby number is not going to be small. So if the Rossby number is small, that implies that the time variation is the order of a tenth or less. So, I mean, the Rossby number small implies that there's, you know, a geostrophic balance, which implies at sort of the 10% level that thermal wind would apply, I would think. So
we have done some theoretical study where if you are stably stratified, if you are subadiabatic in your core, for instance, all those mechanisms still work. So there is no problem with the stratification. It just, you excite gravito-inertial waves instead of purely inertial waves, but your perturbation of the buoyancy field follows the wave motion, basically.
So the time scale of the variation is fast then, or what's the? Okay, yeah.
Okay, we have time. Yeah, Michel?
Yes, I was wondering if with your experiments you can evaluate the power dissipated in the fluid.
That's something we would love to do, but it's very difficult. The amount of dissipated power is about the same as the noise on all the bearing and so on. Yet that was a very difficult trick when we built these new experiments. We have absolutely no idea of what the size of the motor should be. So we just took the biggest one. That's the nice thing about ERC. You have a lot of money, so you don't have to think so hard. And that's something we will try to do. But it's a very nice motor with low noise. And we hope to measure it. I know one guy managed to do it in the 70s, measure the torque on the motor in a precession experiment. I don't remember right now in which paper it is, but there are some measurements. You will find it in the Kerswell paper that has just been published in JRL. He mentions those measurements. So there are a few measurements, but it's very tricky to do experimentally.
Okay, any more for any more? Okay, let's thank Mikhail again. And we'll come back at 10:02.